Thank you for joining the webinar, and I'll be happy to present today the fundamentals of desalination. I'll talk about the main issues associated with desalination, including what are the water, what source of water requiring desalination, properties of water that have impact on desalination. I'll touch on the main desalination technologies that are currently implemented around the globe, and talk about water recovery and cost of desalination as a major driver or maybe limitation for implementing more desalination. And I'll talk about a few issues associated with desalination and complete the presentation with introduction to a few of maybe future technologies. So you might all know that we're using desalination for seawater and for brackish groundwater, but we're using desalination for much more than that. A few examples are industrial water, in mainly on the high purity side. You can think about the electronic industry, food and beverage, dairy industry that requires separation of salt from water, but also other constituents from liquid streams. We're using more and more reverse osmosis for advanced treatment and reuse of wastewater, and in some cases we also see surface water desalination for removal of specific dissolved solids. So what are the things that we're trying to remove with desalination? Usually it's a group of things that we call dissolved solids, everything that will go through simple filter, but will precipitate or will not be removed by conventional processes. So, for example, different salts or ion, heavy metals, nutrients, hardness as calcium and magnesium, silica, and lately also more and more organic contaminants of emerging concern like pharmaceutical, personal care products, pesticides, and things that we find more and more in our waterways. There are a few colligative properties of ionic solutions that play a major role in desalination. These are properties that depend on the number of solute molecules or ions in solution, but not on the nature of these solutes. So two of these properties, osmotic pressure and vapor pressure, are playing a big role in any desalination process that we are currently implementing. And I'll start diving into the different techniques and methods to do desalination. In one group of desalination processes, we are taking advantage of vapor pressure of water. And here on the graph, you can see the vapor pressure of different types of water as a function of temperature, and temperature plays a major role in vapor pressure of water. This is the pressure where water or solution or any liquid will boil. But I think the nice thing that you can see here, and that's the nice thing about evaporation processes, that as we increase the salinity of these water, it very minimally impacts the vapor pressure of water, which tells us that we can desalinate water and recover a lot of water from saline water by evaporation. The way that it's implemented is by, for example, a single effect evaporator, where on the left you can see a steam or a source of heat that comes on one side of a separator. On the other side you have different feed streams that get evaporated and condensed, producing distillate, and on the bottom producing brine. That has limited capacity, and therefore we connect many of them together into something that's called multi-effect evaporator or multi-effect distillation, where we take feed water and go from one stage to another and recovering the heat from one stage and doing distillation in the adjacent chamber at low temperature and also at lower pressure to achieve as much distillation as possible. Another option is multi-stage flash evaporation or distillation. In this case, we are recovering some of the heat of condensation on the top and doing recovery of water. On the left, you can see some addition of energy or heat into the water, and the water go into the open, the bottom of the chamber where it evaporates, produces vapor, and condense on the top. Again, here also we are using some vacuum on the top to enhance the evaporation and enable evaporation at lower temperatures. Another option of distillation processes and more commonly used and consider having a little bit lower cost of desalination is vapor compression distillation, where the vapors are taken from the top of the chamber, compressed with a compressor, and that enables a much faster liquefying of the water and production of distillate at the bottom, and with some heat recovery inside the distillation process. So these are different evaporation methods, and they are used around the world, and I'll later on talk a little bit about the distribution of these processes around the world. I want to jump into another way of doing desalination, and that's through separation through membranes. In this case, we're using unique membranes that have unique properties that allow some constituents from our feed solution to go through the membrane and become a permeate or product water. As depicted here, you can see that the membrane is designed to allow more flow of the constituents that of interest, in this case the solvent or water, and it also shows you that some constituents that we want to reject or retain on the membrane manage to cross the membrane, and that's part of the nature of these membranes, that they are not perfect, and they allow some ions or molecules to go through. And when we do desalination, we use very unique type of membranes, reverse osmosis or nanofiltration, and I'll talk a little bit about the concepts around it. In osmosis or reverse osmosis, practically we are dealing with the natural phenomena of osmosis or diffusion of water from feed that has low salinity into a concentrated brine. In that case, water will diffuse through this membrane into the brine, dilute the brine, and increase the hydrostatic pressure up to the point that it will be equal to the osmotic pressure. And what we need to do in reverse osmosis, we have to oppose or to resist this osmotic pressure in order to produce water from the left to the right and produce clean water. And this is depicted in this slide, where in seawater that have approximately 35 grams per liter of total dissolved solids or salts, we need more than 350 psi in order to press the water and push it against the osmotic pressure and produce clean water. This is a nice spectrum of different sizes of contaminants or constituents that you might find in water. And on the bottom, you can see the domain of reverse osmosis and nanofiltration, and on the top, the size of constituents that they might reject or retain on the membrane. And you can see that reverse osmosis and nanofiltration can retain simple salts, metal ions, dyes, sugars, and everything that has this size. With reverse osmosis being more tight membrane and nanofiltration being a more loose membrane that can reject some of the small ion like sodium chloride, but very well reject calcium, magnesium, and large organic molecules. When you look at these processes, this is giving you the range of operation pressure and water flux or productivity of water through this membrane. And so while you can see that the productivity of these membranes is almost the same, you need much higher pressure and therefore higher energy to operate reverse osmosis. And again, reverse osmosis can be different things, and there are different reverse osmosis membranes, those that work for high salinity and those that work for lower salinity. Going to another unique membrane process that uses electrochemistry in order to do separation, in this case separating the ions or removing the ions through the membrane and not the water. In this slide you see just the general phenomena where we produce electric field between two electrodes in water. They will attract, the cathode will attract the cations, and the anode the anions, and will be able to leave a void in the middle without salts. This is nice but inefficient, and for that people developed the process. It's called electrodialysis, where the two electrodes are separated by pairs of membranes. C stands for cation exchange membrane, and A stands for anion exchange membranes. And in bottom you can see that the cation exchange membrane allow cation to go through, and the anion exchange membranes allow anions to go through. And what happened over time is that you create sections where you don't have ions, depleted of ions. This is the diluate, where this is the water that we want, and all the other ions are concentrated in the other channels, and that's what becomes the brine that we have to dispose of. So when we look at the spectrum of what do we want to desalinate and how much it costs, you can see that on the bottom left we have different types of reverse osmosis and electrodialysis. They can work pretty well at salinities less than 7% or 70 grams per liter, and the cost of desalination is somewhat around or less than 10 kilowatt hour per meter cube of water produced. If you want to desalinate with more concentrated water or have high recovery, we'll go into these evaporation processes that can reach higher recoveries and higher TDS, but at the cost of more energy. So this is a nice slide that shows you the approximately current distribution of the different processes around the world. And as you can see, reverse osmosis is by far the largest technology or implemented technology around the world, followed by the distillation processes at around 80%, 20%, and then nanofiltration used mainly in industry, and a little bit more and more in groundwater, brackish groundwater desalination, and very small portion of the electrodialysis, because electrodialysis is really limited to low salinity water. Water recovery is a major issue in desalination. Water recovery relates both to the economy of desalination and how much water we will be able to sell, and also having a big impact on environmental issues like what do we do with the brine that we generate during these separation processes. And here is an example of how we calculate recovery. In this case, if we have 20% recovery of water on each stage, we are producing 48 or close to 50 gallons of water out of 100 gallons that we sent into the system, and we have close to 50% recovery. Again, the implication of that is that we have 50% of the stream becoming brine that we need to dispose of or do something with, and this brine also receives some pretreatment, which means that there is a cost associated with preparing it and then disposing it. Again, another example, if we want to do seawater desalination, and most seawater desalination operate at approximately 50% recovery, and then when you consider that the osmotic pressure of 1 gram per liter of salt is approximately 10 psi of osmotic pressure, we usually need more than 700 psi in order to desalinate seawater and achieve 50% recovery. This means, again, brine management and a lot of energy cost. So this is the implication of trying to operate at high recovery. So for example, with seawater or brackish water reverse osmosis, we can do 60 to 85% recovery with moderate cost of operation and a relatively high cost of disposal, brine disposal. What we really want to achieve is zero liquid discharge or very high recovery of the water, but that means much higher cost of operation. And in between, we have emerging technologies that we try to promote that have that can reach more than 90% water recovery. When we look at the cost of desalination, highly variable cost, here we break it into the capital costs, and that's based on gallon per day installed. in operating cost, operating and maintenance costs based on per 1,000 gallons of water produced, and that gives you a cost for meter cube or 1,000 gallons produced going between 20 cents per cubic meter for nanofiltration and can go up to $2 per meter cube for seawater reverse osmosis, which can be pretty high. I think the next slide is very, very interesting because it shows you the pretty much the largest desalination plants around the world, and you can see differences in costs per meter cube of water produced. I don't have here the new desalination plant in San Diego, and Jessica will talk about it more, but it's around $1.50 per meter cube, like the one in the Bahamas here. And there are different reasons why there's cost difference between these desalination plants. This has to do with the energy cost to operate them, cost of brine management, project costs, including engineering, permitting, and environmental compliance, tax credits, and size of the plants play also a big role in the cost of water. Quickly talking about pretreatment, all these processes cannot operate without some sort of pretreatment to remove major constituents from the water that can compromise the process. These are suspended solids, microorganisms, organic matter, and other ions that can harm the membranes or the materials in the process. This is an example of a water potable reuse application where we are using reverse osmosis as a core process, and you can see from the left we have wastewater treatment plant that does the conventional process, going into microfiltration, addition of chemicals, and only then we have reverse osmosis and even distillation on the site for salt management. Energy recovery is a major issue in desalination, especially in reverse osmosis. It's embedded in distillation processes when we recover heat from one stage to another. That's there, but in reverse osmosis nanofiltration, energy recovery is very important to make the process economically viable. And there are different ways to do it, and when I say energy recovery, it means taking the high pressure concentrate and instead of just going through a valve, going into a device that will recover the energy and send it into the incoming stream and enable partial recovery and therefore operation with smaller high pressure pumps on the left. So this is an example of one company that makes this pressure exchanger. Another company that makes this dual work exchanger energy recovery device. This is big pipes that have big pistons that moving and transferring the energy from one stream to another. Clark pump is another type of energy recovery device that again takes the pressure in the brine and transferring it to the incoming stream. Desalitech is another, the closed circuit desalination, another way to work with less membranes but with much higher velocity of the stream on the membrane, reducing some of the problem associated with the concentrate in these membranes. And another way to recover not the energy from the pressure but recovering the energy from the salt is a nice process that's called pressure retarded osmosis that's actually recovering the chemical energy in the brine going into freshwater or seawater and recovering it as a pressure energy in a turbine. One of the last slides, concentrate management. Concentrate management is a major issue. In coastal installation, it's less of an issue. Most of the desalination plants send the brine back to the ocean, and there are many studies that show that maybe locally, very small location, you'll have some issues with high salinity, but usually the salt will diffuse very quickly and the ocean will absorb it. Inland desalination, there are different options to deal with the brine. The best are probably deep well injection, but different options have the cost associated with them and environmental issues associated with them. And quickly into future technologies, just example of a few of them: distillation through membrane, membrane distillation process using very hydrophobic membrane, Teflon or polypropylene, membranes that have small pore that allow vapor to go through, but not the water. There's a lot of research going all over the world trying to promote this technology. Humidification, dehumidification process taking again advantage of waste heat or low-grade heat sources to recover humidity from air. And more and more you see at MIT, University of Texas, in Europe, people looking at desalination on a chip using electric field to separate salts from water. And with that, in summary, desalination is used for salt removal not only for seawater and brackish water, but for other constituents and for other industries. Development of new membranes by membrane company focuses on increasing fluxes, increasing rejection of different solutes, and increasing the resistance or resiliency of the membranes to resist degradation. Reverse osmosis is becoming a core process in enabling potable water reuse, very important in California, Texas, and other places that have to deal with droughts. Desalination is becoming very affordable at 50 cents per meter cube. It's not cheap, but it's not too expensive, and energy efficiency and better membranes are important factors that enable it. And brine management is an important issue, especially at inland installation, where you have to do something with the brine, and that drives a lot of research and development in this area. Thank you for listening, and I'll be happy to take questions at the end of the webinar.